So we'll need a coordinate system such that we're saying, because we're trying to say the center of mass in the x direction is at a certain point, but you have to measure that from somewhere. So we need a coordinate system, number one, and then we need to figure out how much mass both of these have. So this one, for example, we could pretend this was a whole bunch of squares. Well, not a whole bunch, but a few squares. It would be 5 2x2 squares. You okay with that? That rectangle has 3 of the 5. You got that? So what fraction of the total mass will this bottom rectangle have? 3/5. So it has 3/5 of the total mass. Call this one M2. It would have 2/5 of the total mass. For our coordinate system, let's make the bottom left-hand corner the origin. So our x-axis will go along the bottom edge of our object, and the y-axis will go along the left edge of our object. To use the center of mass equations, we need to know the Cartesian coordinates of this point. We're treating this rectangle as if it were one point mass. Where is it? What is its x position? Y position?
1.
Fabulous. Sorry, that's not working very well. What about the position of this one?
1, 4.
Okay. So the x position of the center of mass is the x position of this dot times its mass. So 3 times 3/5 m plus the x position of this one times its mass. So 1 times 2/5 m all over the total mass. So we get 3 times 3, 9/5 m plus 2/5 m all over m, which is 11/5 m over m. M's cancel, 11/5. So just over 2 is where the x center of mass is, 2.2. That means the x center of mass is somewhere along that line. Now, it doesn't tell us exactly where it is, unfortunately. But it does tell us it lies along there somewhere. Are you okay coming with that, up with that value? Or are you okay understanding that it's somewhere along that line?
Is it always going to be as simple as this, as being able to cut it up like that, in cases where you need more and more complicated?
At this point, we'll just have it where we can cut it into pieces. Since Calc 2 is not a prerequisite for our class. The y center of mass. We need to take the y position times the mass. So 1 times the 3/5 m plus the y position, the 4 times the mass, all over the total mass. And again, the masses are going to cancel, so we get 3/5 plus 8/5, which is conveniently 11/5 as well. So just over 2, so So this is the y center of mass line. Where those two lines intersect is the center of mass. So this object, the center of mass, is actually just outside that little corner there. It's not physically on the object itself. This is a rigid boomerang, similar to what a boomerang is. The center of mass of a boomerang lies just inside the curvature of it.
So if the z was in the middle, that means, you know, if it was
Right.
5 long, it would be at 2.5.
Correct.
Plus that. And if you threw it on an arc, even though it may oscillate, do all kinds of things, for that center of mass,
Would follow the nice parabolic
but the center
trajectory.
may be in an oscillation, right? But it would follow,
No, the center of mass,
will not oscillate. It'll stay right.
well,
Yeah. You got wind and stuff, so.
yeah, with drag and stuff, the center of mass actually will follow the nice parabola. It shouldn't
So in a vacuum.
wobble. Now it's important to know where the center of mass of an object is, because when we talk about the different momentum, we're going to talk about momentum, we're going to talk about forces, we're going to talk about energy. It's important to know where the center of mass is. For example, I have a little object here, two little cones. The mass is distributed uniformly, so the center of mass is inside in the geometric center, so it's along this line in the middle. I have a little track for it to roll on. This end's higher than this end. Yet, if I take this object and put it at the lower end, it falls off. Try that again. It appears to roll uphill. The track goes up. But the center of mass is going down. Okay, so energy is still being conserved. The center of mass has a lower position to get to. When we look at energy, gravitational potential energy, for example, we need to know simply where the center of mass is. When we say mgy, y is the location of the center of mass. If the center of mass has a lower position to get to, it will go there. And that's what's happening here, is the center of mass is going down. So energy is still being conserved. Okay? When we talk about forces, for example, the force of gravity. Now, this whole meter stick, every piece of this meter stick has mass. So technically, the force of gravity is acting everywhere on this meter stick. It's pulling on every single little segment of it. But the overall motion that the meter stick experiences is as if the force of gravity only acted at the center of mass. So rather than talk about the force of gravity acting everywhere over the meter stick, we can treat it as if it were acting just at the 50 centimeter mark. And look at what happens there. Okay? So the force of gravity, we can treat it as if it were just pulling on the center of mass. So center of mass is important to be able to locate it. Now, most of the objects we're going to talk about are going to be uniform. So we'll know that the center of mass is in their geometric center. Or they'll be simple enough that we can find the center of mass easily. Okay?